Welcome back, everyone. We will now begin the third part of the webinar series. Again, this webinar will be presented by both myself and Michael. In the final webinar, we will give a detailed example of the asymmetrical data integration approaches. We will begin with an fMRI-informed EEG analysis. I will give an introduction to the general linear model that we will use to extract a peak activation cluster from a region of interest. And then Michael will use that information to perform an EEG source analysis in Analyzer. In the second example, we'll use the same data set to perform an EEG-informed fMRI analysis. And there, Michael will cover how to extract or how to do an ERP analysis and extract information from our EEG data that I will then use to parametrically modulate the hemodynamic response in the fMRI data. So let's begin with the fMRI-informed EEG analysis example. Here we see an overview of what steps we do to integrate the or inform our EEG analysis based off of our fMRI data. We use the spatial information obtained from statistical parameter maps from the bold signal changes for an event-related paradigm. In this case, it'll be for the high contrast checkerboard, and then use it to spatially constrain or guide our EEG source analysis. We need to recall that due to volume conduction through the head and limited sampling or spatial sampling of the scalp EEG, we have the ill-posed inverse problem. And this requires a spatial constraints and regularization terms. So we can use our fMRI spatial data to better inform our regularization criteria within the EEG source analysis. We are making an assumption here, or several assumptions, that includes that the fMRI signal at a given location does carry information about the local dipole activity, and that the neural generators of scalp recorded EEG do trigger some kind of metabolic response that we would then also see in fMRI data. Now, one frequent method for evaluating event-related bold response involves using a general linear model analysis. In a GLM, we treat the observed data as a weighted combination of model functions or predictors and noise or error. And in fMRI data, we use, or our observed data would be that of our voxel time series, as we can see here. And this is now made up of predicted bold activation to some kind of stimulus onset, such as a high contrast or low contrast checkerboard, and background activity or noise. And the shape of the fMRI signal is known as it is determined by the onset of our experimental condition, but the amplitude or expected amplitude to a response is not known, and this is what we now will estimate. Note that the GLM is performed independently for each voxel, and we will now focus on how we can create one of these predictors of interest. So in the general linear model, we need to define the model functions, and we can do this by creating a design matrix that specifies the response to each condition. The onset of predicted response is defined by the onset of the checkerboard in our data set. And since the duration of the checkerboard that we had was equivalent to 1 second, and the TR or acquisition time of our fMRI brain volumes was also 1 second, we can model the onset of the checkerboard as a stick function, as we can see here in black. Now we can see that currently the stick function isn't very representative of the voxel time series that we see in blue. And this is due to the fact that there's the slow hemodynamic response in our voxel time courses, and we need to also consider modeling this. Now, there's a characteristic hemodynamic response function that has been modeled off of neurovascular coupling properties, and we can use this to then convolve it with our stick function here that we created earlier. And now we have a model function that looks like this in orange, and we can see it's starting to look a lot more similar to our underlying voxel time series in this particular graph. I have shown an example of how to create one model factor within our GLM model. However, we do have several conditions in our paradigm, and we may want to consider also modeling other factors that influence the data. So we had two conditions that included the high contrast and the low contrast. And for one session, we can then see here we modeled the onset and our predicted response for both the high contrast and low contrast condition. And on the y-axis here, we have the 390 scans, which were acquired for one session. In our design matrix, we can then also add nuisance regressors. And these are sources of variability or other sources that can explain some of the variability that is not defined by our experimental design, but is present in our observed data. So in this example, I used the motion parameters that we had obtained in the pre-processing earlier. These correspond to the three translation parameters in the three spatial axes and the rotation parameters also for the three spatial axes. We could also consider modeling respiration, for example, since we know that respiration rate also influences fold fluctuations. Or, as I had mentioned earlier, this is also where we could model scanner drift in our GLM model. We also need to consider that we acquired data for 5 sessions within one subject. And usually when setting up a GLM analysis, we want to analyze the data across all different sessions for one given subject. So what we can do is we can concatenate our design matrix for each individual time series, and one of the resulting matrices or design matrix that we're left off with would look something like this, where we have our concatenated time courses on the y-axis and the different model functions for different sessions on the x-axis. Once we have the design matrix, we then need to estimate our parameters or calculate them. And what we essentially do is we need to fit the designed model to the data by estimating the beta parameters, which get estimated by minimizing the sums of the squared residuals. And here, the magnitude of our parameter weight indicates the strength of the effect or contribution of the corresponding predictor variable on our observed data. A larger absolute value will signify a stronger effect, and the sign of the parameter weight, so whether it's positive or negative, will indicate the direction of effect. We also may want to pay attention to the residual variance, as the residual variance will indicate how well the model that we just estimated fits the actual data. And if there's a lot of residuals, as they're often termed, or very high residuals, then that may mean that our model does not fit our actual data very well. Once we have estimated the parameter weights for all of our voxels, we need to perform some kind of statistical analysis to see in which voxels the parameter estimates for a given predictor function are statistically significant. And we can do this by performing either a one sample t-test if we're interested in examining one condition, or a 2 sample t-test if we're interested in the linear combination or comparison of 2 experimental conditions. What we then see reported as regional activation maps in papers are the voxels that have beta estimates that had a t-value that is statistically significant. And here we see an example for what the regional activation maps would look like for the high contrast checkerboard condition, the low contrast checkerboard condition, and then the comparison of high contrast versus low contrast. Now, note that we have performed the statistical test for each individual voxel. And within a given fMRI data set, we have tens of thousands of voxels. So we need to consider that the greater the number of statistical tests we have performed, the greater the chance there is that we are performing a type 1 error or have false positive results. For example, if I had an alpha value of 0.05 or a p-value of 0.05, the number of false positives we would have for 10,000 voxels would be 500 voxels, and that could be a significantly large region. So we may want to consider correcting for multiple comparisons when performing our GLM analysis, and we particularly should consider this if we then want to use the fMRI data to make some kind of informed decision on our EEG source analyses later, as we wouldn't want to accidentally constrain our EEG sources, for example, on a false positive. In this particular data set, I corrected for multiple comparisons by using a family-wise error correction, and this then resulted in peak or activation maps, as we see here for the high contrast, the low contrast, and then the high contrast versus low contrast comparison. And what we can already see is that the overall region or size of these activation clusters has become a bit smaller. And then I used the coordinates as indicated by these crosshairs for the peak activation of each one of these conditions and read out their MNI coordinate space along with their t values and the overall cluster size here. And this information will then now be used and implemented in the EEG data analysis. And the next part of how to implement that will be covered by Michael.
Thanks, Celia. Then let's go on. Just give me a second to share my screen. Okay. There we go. Okay. Good. Let's actually start where we ended with our processing pipeline. So in the last session, we talked about the pre-processing of the data. However, now we also have to look into what came afterwards. So we're having an ERP analysis here. And actually, before doing the fMRI-informed EEG analysis with source analysis, we actually need to have our ERP analysis. So also this I have already prepared, and as in the past session, I will talk you through this. So what you will see now in the analyzer pipeline are these additional nodes, and I just want to highlight a few before switching to analyzer. So what we have here is now split in the pipeline and parallel branches, which is a common thing because after the common pre-processing, we now have actually two different conditions, and those conditions are then further analyzed in parallel. So in our case, we have the condition for the high contrast and the one for the low contrast. Then we have some post-processing that is happening. So post-processing in the sense of still treating with the quality of the data, but after the data has been epoched into trials. And then in the end, we're having our ERP here. In the case of our visual stimulation from the paradigm, we would be looking for a visually evoked potential to the checkerboard stimulation. And then we have some additional nodes, but let's actually now go to Analyzer so that I can show you very briefly what are the differences now. So we have here now, that's the last node of the pipeline, of the pre-processing pipeline. So now if I click on one of our segmentation nodes, you see actually how the display changes here in Analyzer. We're now having one grid box per channel. And if you highlight one by double-clicking, you see now the data has been epochhed from 200 milliseconds pre-stimulus until 1000 milliseconds after the stimulus being at time point 0. Then we have here the baseline correction as the next point. So the baseline correction is there to deal with offsets between trials in case that the amplitude level just linearly increases or decreases over time. So we would have offsets between trials, and we want to have them at a zero mean centered. And this is a very common processing step in the EEG. Afterwards, we have another artifact detection node, and this time artifact rejection. This time you see actually raw data inspection is at this point gray out, because artifact rejection is the equivalent of raw data inspection for segmented data. Here we actually now, and I'm going to the operation infos, we use now the amplitude criterion. And this is now because we have treated the offsets between trials here. So the baseline has been subtracted, which means now it makes sense to use absolute amplitude thresholds. And a common thing is to just discard trials that go beyond a limit of 100 microvolts plus minus, and just to consider them as too noisy and not use them in the analysis. And if I double click on this node, you hopefully see now down here in the navigation bar that there are a few of these red shades again, mostly towards the end, because I think I mentioned it before, the data got a bit noisier over time, because the longer the participant is in the measurement, sometimes, the signal just gets worse over time. And this is pretty much what we see here, that more and more electrodes got worse, and this is why we have more data that is bad here in the end. Okay, then we have our ERP. Just want to show you once. And let's look at all channels. Okay, and for instance, here, grabbing this one out because there's a pretty large deflection, PO8. So in a posterior electrode, we have a rather big deflection around 100 milliseconds. So in an area where we would expect something visual to happen. What you can do now is, of course, also mark some data again and use the mapping view as we have done before, and just go over the data and see, yeah, actually here some positivity is arising in the back of the scalp and then vanishing again. Can also mark the whole deflection, and you will also see that there is something going on in occipital electrodes mostly. Just to mention, we have two more nodes here. We have a pooling. A pooling is something that can be quite useful. So at first, this looks like we have exactly the same data here. But then if we go to the end, we added a pool or a ROI, a region of interest. And if you right-click and go to the operation infos, you can also see what is in there. So actually, this pool is built out of occipital and parieto-occipital electrodes. However, more to the right side, because you saw maybe also now on the map that we have a more right-sided distribution. This can help. For instance, you get a little bit of a smoother signal because you're averaging across electrodes. And then this could give you a nicer idea of the time extent of a component, for instance. The other thing that we have here is a difference wave. A difference wave is built by the data comparison transformation that you find up here. So this one is the difference between high contrast and low contrast. So the low contrast is subtracted from the high contrast. Just grabbing out the same electrode as before. And here you now see in black the difference wave, while in red and blue we have the parent data, so the average of the high contrast and the average of the low contrast. You can actually also right-click and say, don't display this static overlay. And now you have basically what's the activity increase between the low contrast to the high contrast condition. So this is something, especially if you're coming from the fMRI world, you might be familiar with looking at contrasts between conditions. So this is basically the equivalent that we have in the EEG. And we're actually now going also to use this node in order to make our data fusion. So we will take information from the GLM that Celia just presented and take the coordinates of the peak voxels of the different significant clusters in this same contrast in the fMRI GLM and use them as input to our source analysis. However, before doing that, let me just quickly go back to the slides and just give you a little bit of a background about what we are going to do now. I will just talk a little bit about source analysis. However, due to the time reasons, and we also have more topics to cover, I will do this in very brief, but if you are interested, we have great materials existing about source analysis with LORETA, which is the source analysis algorithm and analyzer. So there is a webinar recording that you can rewatch, and there's also an excellent tutorial article available that you can also find on our website. However, both links are again in your handout. So just in very brief, when we're talking about source analysis, what we want to do is we want to take our electrical potentials that we have measured from the scalp with our electrodes, and we want to infer from that the neuronal generators of those potentials. And this is called inverse modeling. There are different algorithms available with which you can do this. And each of those algorithms also has an underlying assumption about the different directions. So the direction from the actual neural generators of some activity, and also a physical model about the volume conduction, so how the potentials from the neuronal currents are transmitted, propagated through a medium, which is the brain and other tissues, and then reaching the electrodes, giving rise to our scalp potentials. So this forward model is something that has to be considered when using a source analysis algorithm. However, this is something that is inbuilt with certain assumptions into the algorithm. Okay, let's talk about LORETA, since this is our algorithm for source analysis and analyzer. And here, the first thing to highlight is there are two ways of doing LORETA and analyzer. And you can decide which way to go by asking yourself the question, do you have a priori information about the region of interest? So this means maybe you have this information from the literature, so maybe you know either other people or yourself, you have done experiments looking into this, maybe with fMRI, and you know where to look. However, in our case, we have done EEG-fMRI in a simultaneous measurement, so we will also have coordinates from the GLM and the fMRI data that we can use as a priori information. In such a case, we would go for LORETA as a primary transformation. You can find this in the Analyzer menu under Special Signal Processing. And this will deliver us the source time series for the region of interest that you define. However, if you do not have this information, you can still do source analysis. In this case, you can actually infer the regions of interest by using LORETA as a transient transformation. So you might have seen earlier when I used the mapping view that there was also a point LORETA in this right-click menu. And if you do this, you get a source activation map. So something that looks very similar to what you get from an fMRI analysis if you compare this sketch to this sketch. However, this is also rather blurry, and we will come in a moment to why this is the case. So if you do this, you can infer now from the source activation map where is actually the activity coming from, where is the peak of this activity, and use these coordinates, put them into the LORETA transformation and get a source time series. And of course, if you have done this already based on the fMRI coordinates, you can also then compare these two against each other. So generally, these two modes of LORETA, they are complementary. Okay, let's talk a little bit about this whole modeling that's below the LORETA in Analyzer. So there are a few ingredients, so to say, to this that I want to go through. So the first one is the source model. So this is the source space that is available in the LORETA algorithm, and this is restricted to cortical gray matter and some areas in subcortical regions, notably hippocampus and amygdala. And this is a much smaller and much coarser source model, source space, than what you are used to from fMRI. So we actually only have 2,394 voxels here, and they have a spatial resolution of 7 millimeters. So 7 millimeters cubic is each edge of this voxel, or the volume of the voxel. And so this is much, much coarser than what you get in fMRI. Additionally, there are a few other model ingredients. So we have the anatomical model. LORETA in Analyzer is based on the MNI templates that you are probably aware of if you have done fMRI in the past. So what we have here is not a realistic individual anatomical model that you could use like anatomical MR scans for, but what we have here is a model based on standard templates. Also, the head model is based on a rather simplified standard model, which is a 3-shell spherical head model that is registered to the Talairach atlas and based on the MNI brain. As you can imagine maybe from following Celia's talk earlier, all of this has also to be expressed in the same coordinate system like in the fMRI preprocessing. So anatomy head model, but also the electrode positions have to be in the same coordinate system. So some co-registration is also happening here. Okay. Let's talk about the inverse method. So everything that I just mentioned is just a given when you are using the LORETA in Analyzer. And LORETA is one of the very established distributed source imaging methods. So distributed means in this case that it just looks at the activity in each of these small parcellations of the brain. So imagine a 3D grid of these 2,394 voxels, and then you have like a small dipole in each of these grid points, and we are estimating the magnitude of each of these dipoles. And the assumption that LORETA makes is neighboring sources tend to be synchronized, so they have a similar orientation and magnitude. And this is necessary that LORETA does this, because if we do not put some a priori assumptions in here, you can really not get a unique solution out of this, because this is a problem that is ill-posed. There are unbelievably many, maybe indefinite configurations of neuronal sources that could give rise to the same potentials on the scalp. So therefore, we have to limit somehow this solution. And this is by assuming, for instance, this mathematical constraint here, and also by having this limited source space. So what is done mathematically is simply assuming maximal smoothness of the source intensity values. So therefore, you're getting this very blurry blobs out of LORETA, these source activation maps like down there, instead of like point sources for this frontal and occipital activation. So the smoothest possible unique inverse solution is what you get out. And this is also where LORETA gets its name from. It's a low resolution electromagnetic tomography. And the nice thing is, though, even though this is low resolution, you get this blurry blob, you still get the location of the maximum activity for each time point. So you get a coordinate of this voxel out of it. And therefore, you have some similar information what you get for the fMRI, where you also get a peak activation voxel of a cluster. Okay, let's now go back to Analyzer and now actually do this. So I will do a demonstration of how to apply this. And as I said before, I'm going to use the difference wave that we have here. And I'm actually now starting from the side of integrating the fMRI information directly with LORETA. And then later on, I'm also going to use the other pathway that I mentioned, and then we compare the two. So the first thing I will do is I go up here to LORETA in the special signal processing part of the menu. And let me just quickly explain this this menu here. So first of all, you have here the section where you define your regions of interest, and this is empty by default. So what you would do is you would insert a region of interest, give some name. I just leave it now like this, and then you can add something to that region of interest, and you can define it, for instance, by adding a lobe or a gyrus, so rather large areas, something smaller like a Brodmann area. But what you also can do is you can move those sliders here, and then you see how those planes here are moving through the 3D volume. And also what changes is the coordinate here. The sliders point to this coordinate now. And now that I have selected the coordinate this way, I could also say, please give me a block or a sphere around this coordinate, or give me the nearest voxel. So what you would do is build this up manually. However, to save some time, I have already prepared this. So let me actually remove this again. And now I will just use this load ROIS from file. And it opens up this menu. So it goes to my workspace and analyzer. Then I have to switch here over to the XML file because this is how I stored it. And then I have two files here, one for now and one for later. So this one is the LORETA coordinates from the fMRI contrast, high contrast minus low contrast. So I'm loading this. And here we go. So I have defined 3 regions of interest here. And you can see now if I click on them, how this dot is appearing here. And if I click on a different one, it moves somewhere else. So those are single voxels because what I did here is I defined a coordinate that you see here. And I said, give me the voxel nearest to that coordinate. So it's just one voxel. But if you point your attention to here, you see actually what I wrote here, or the coordinate that I selected, and the coordinate that we have here in visible in this map, and also where the activity is extracted from, is a different one. And this is now because source model of LORETA is a different one than of the fMRI data. So it just happens so that this voxel that I got out of my fMRI GLM is not part of this source model. So it jumps over to the next coordinate. And therefore, also this label might be a little bit different. So what I wrote up here, those labels, BAs 30, 18, and 19, is what I got from here. So this is referring to the label of the actual coordinate where we landed in the source model of LORETA and from where we took out the activity, the time course of the source. So this is based on the Talairach atlas again. And so what we have here, if you're familiar with brain anatomy, Brodmann areas 18 and 19 are actually visual areas. So they are in the secondary visual cortex. And Brodmann area 30 is in the retrosplenial cortex. So if you look at this, you see this is a little bit more anterior and a bit more central than the others. So still close by. Yeah. So this is now what we have defined here. And now we can simply extract the current density magnitude from this. This is usually what you extract as a measure with LORETA. So that's what I do now. I just click OK. And this doesn't take very long. And here we go. I'm just renaming my node here as I have done with the others. So this is now the LORETA based on the fMRI contrast HC larger than LC, so that I know later when I do the other one which one is which. So now you might wonder, why don't I see anything here? The reason is the unit has switched here. This is now no longer microvolt. This is microampere by square millimeter, and this is on a much lower scale. Therefore, you actually just have to upscale, and then you see the potentials here. So what we can now see, for instance, is if we are looking at the area where we would expect something. So remember, we are looking at the visual potential around 100 milliseconds. So here we see actually around 100 milliseconds. So that's here. There is something in all of these 3 time courses. There is definitely a bump. So this is some source activity that we could now actually export from this signal. So we could now get, for instance, the peak or the mean amplitude around this signal, and then do further things like statistics with that. And if we also overlay the 3 of these, so if I right click here and I say switch view and do butterfly view, you can actually also see, so especially the BA18-19 time courses, they are almost identical as it looks. And the one that is a bit further away, the voxel, looks a little bit different, but still, I would say the dynamics of this signal are very similar. Okay, so let's now do it the other way around and see if we can actually get some similar information from our non-fMRI informed analysis. So to do this, I would actually go one step back and now simply use the transient LORETA to see what I can infer from the source activation map of the LORETA in the EEG. So for this, it's actually not mattering for this. If I use P08 or a different electrode, I don't have to focus on an electrode for this, but it's just easier if it's bigger. So this will take into account all positions, all valid positions of electrodes on the scalp, which means it really doesn't matter if I do the transient view on this electrode or on any other, the result will be identical. So let me therefore just click here, and I'm just clicking so I get only one time point, and I say LORETA. This just needs a second to compute. And let's see. So here we are at the beginning, almost around 100 milliseconds. So you can see here it's at 114 milliseconds. And you see definitely there is something happening frontally, there is something happening posterior areas, and at this point here, the maximum is in Brodmann area 10, so that's something in the front. Well, let's see if I also get some, oh, yeah, here, okay, if I go a bit more earlier, I get 17 occipital lobe, and let's go in the other direction. Yeah, okay, so in the very beginning here, in the small dip, which is even a little bit closer to this, I get this Brodmann area 17. So this is definitely something I would be interested in, because like Brodmann area 18 and 19, Brodmann area 17 is visual cortex, even primary visual cortex. So this could be something to look at. So you can, of course, do this here in a data point by data point fashion, but you can also do the transient view based on a longer time window, getting like the whole peak. However, you see now that you actually get a little bit of a diminished blobs here, because now you use an average across this whole time window, so from 116 to 234 seconds. So again, this is then a little bit like averaging out some extreme values, and not that much will stay. So I would actually say it makes sense to look into this voxel of Brodmann area 17. Oh, yeah, I have it again. So which is what is the maximum at the very beginning of this deflection that is happening here. And so now I can use this coordinate to look into this in the same way as before. So for this, I just have to re-raise the LORETA transformation. And again, I have prepared this, so I have tried this out before, and I created, based on the same principle here, these ROIs. So I remove the ones I have used before, and I load my different file. You have seen this before, which is here, BA17. Okay, again, I have used now the coordinate where we landed. You see it here, 4 minus 81, 8. This time also, that's the one that we see here, because this is inferred from the EEG data with the source model of analyzer. So of course, the coordinate that I see here is part of the LORETA source model. Here I used now a different extraction method, so not nearest voxel, but sphere. However, just to show you how you can come to the same result with this, I use a sphere with a radius of 7. And you can see this is still one voxel only here, one dot, because remember the voxels have an edge of 7 millimeters. And therefore, if I would now increase this radius to something larger than 7, then more voxels will be added to this. I've also extracted here BA17 left and right, so the whole of the area, of this Brodmann area, but separately for the two hemispheres. This makes probably sense rather than using both of them together, because we saw already in the mapping view that there is a bit more of a right-sided focus in the EEG data. So therefore, it's a good idea to split this up. And again, it's also a good idea in this case, as in the case before, to have 3 separate ROIs here, because otherwise, if I put all of these in one ROI, you will just average over them, and then you will only get one source time series. So I will now click OK again and extract this. Again, this will not take much time. There, it's done already. I will again rename this. This time it's the EEG-derived LORETA. And again, you don't see anything, but if I scale up, you see something more. Also here, let me do the switch view to butterfly. And you see again, the 3 have a very different time course. This is not surprising since they are all in like the same Brodmann area, though across 2 different hemispheres though. The largest times amplitudes you get from the peak activation voxel, which makes sense again. This is just one voxel and it's the maximum voxel. And then the others are a bit lower because you average across many voxels. And not surprisingly, you get higher activity from the right side than from the left side. So you see on top here, if I hover over something, you see the one which I hover over is in like with a frame around it, so you know which one is which. Okay, so let's now do the following. I'm actually switching here back to the grid view, and I'm closing now my other nodes here and just keep open my 2 LORETA nodes. Also here I switch back to the grid view. And now I have only these 2 open, and I will use this different visualization to tile my windows vertically, which is a nice way here of comparing them left to right. So now here on the left side, those are the time series extracted from the fMRI. Those are the ones from the EEG. And if you are looking now for the time course, especially I would say in BA18 and 19, how similar this looks to the time course that you get here out of BA17. So you see, therefore, there is something very similar happening here. So this is not very much different. It's probably also, if I look at this peak here, 102 milliseconds, and I look here, 89 milliseconds. So this is a very similar time course. So this is reassuring. The comparison shows that both pathways deliver something like complementary information. And however, by using the fMRI peaks, I get something that is a little bit more, let's say, localized than what I got out from the EEG, because I have a bit more of a diverse information here from the fMRI clusters where they are, while I would, due to the Corsa model in LORETA, probably not get this nice spatial resolution inferred from the transient LORETA. So this is definitely a plus. So let's just sum this up on the slides. That was the first part of our fusion analysis. So EEG source analysis can be informed by features from the fMRI GLM, and the MNI coordinates of significant clusters can just be used as a priori information. Important thing here, they are MNI coordinates. LORETA is an MNI coordinate, so therefore this works, of course, because we're in the same space. We have two ways of running LORETA and Analyzer. The transient one, when you need to infer your regions of interest from the source activation maps. The result of these is heavily smoothed just due to the properties of LORETA, but you still get the coordinate of the maximum. Or you use the LORETA transformation and you can extract a source time series either based on the transient LORETA results or using your fMRI a priori information or using information from published literature. It is important that LORETA should be applied on well preprocessed data because you want to have a nice signal to noise ratio. So you shouldn't just put that on unprocessed data. And also time domain data, it says here. So this is something very specific also to our LORETA analyzer. This requires time domain data. So you can't apply this to frequency or time frequency domain data or anything else like t-values or so time domain data. However, the result is then also a source time series that you can process further. So you can use, for instance, time domain exports like you would use for the ERP. And just to highlight it again, the source spaces are different between LORETA and fMRI. So the one in LORETA is much smaller and less fine-grained. So 100% overlap between the regions of interest and activation clusters might simply not be achievable. And also the nearest voxel in LORETA might actually fall under another anatomical label. And what we actually didn't do here is check the anatomical label for the voxels in the fMRI. Of course, you can do this and also compare this and then see also if this happens or not. Okay, and then with that, I would actually hand back to Celia, and we would be now looking into the next approach, which is EEG-informed fMRI.
Okay, hopefully this will work. Okay,
it is typical.
As we could see now from the results that Michael presented, we used fMRI spatial priors to constrain the EEG source data, specifically with LORETA, and then looked at some of the time series. And what we saw specifically in this example is that the time series did look very similar for our source constrained data, or kind of the from the fMRI information, as well as the EEG data that we just source localized using the transient LORETA transformation, which is nice because we do see similar results. But what we also noticed in the fMRI-informed source reconstruction is that the overall time course was a bit more defined within the given features that we had in it. Which is something that we would possibly also expect from doing an fMRI-informed EEG analysis. There are, however, a few things that we should consider, and this is something that is now going to be more applicable to general fMRI-informed EEG analysis methods. We should first of all always ask ourselves whether the fMRI spatial constraints that we are using on our source analysis are how they reflect or impact removing faster acting EEG sources. So we have to consider that EEG can acquire much more instantaneous fast neural responses, and due to the low temporal resolution in the fMRI data, we're not able to acquire that in fMRI. So if we are constraining our EEG information based off of fMRI priors, we may lose some of that source information of these faster acting components. Then again, I would like to point out that we always need to consider that we will have reduced signal to noise ratio in our EEG data, which will also influence the performance of our source localization. And we, at this point, then also need to consider whether we are able to remove enough of the scanner-related artifacts from our data to be able to actually perform a source localization in the EEG data. One thing we can possibly check is to see if there's any consistent source that dominates across all of our experimental conditions, as this would suggest that it's coming from a residual artifact that is still present in the data set. And we did see in LORETA that the smallest spatial unit that we could achieve was a 7mm voxel. However, in other source localization algorithms, especially ones where we concede individual dipoles, we need to consider how that due to the low spatial resolution in the EEG data, we should not be placing any dipoles too close together, otherwise, or taking information from dipoles that are too close together, otherwise they are susceptible to crosstalk. Now, we're going to switch gears a bit and use the same data that we have been referring throughout this webinar, but now we will perform an EEG-informed fMRI analysis on this demo data. I'd just first like to begin by providing an overview of how an EEG-informed fMRI analysis is performed. We use information from the EEG data and extract a specific EEG feature that we can then use to parametrically model the amplitude of our fMRI event. So in our case, we have a checkerboard paradigm, and earlier we modeled the fMRI event as a stick function that we convolved with the hemodynamic response. But now we are going to extract an EEG feature for each individual trial and use that to parametrically model the height of our hemodynamic response function that we then can, again, solve or estimate the beta weights using a general linear model, and we then get a subsequent statistical EEG-fMRI covariation map. And now I'm going to hand off to Michael again, who will take you through how to extract our EEG feature of interest.
Thank you, Celia. Let me share my screen 1 second, and then continue. There we go. All right. Okay, so this time let's again look just at a little bit of background about what we're going to do, and then we will again look in the demo about how to extract the information that we're interested in so that we can use it in our fMRI analysis. So so far, we haven't really talked about what ERPs are. In the beginning, Tracy gave also a short description. However, ERPs are a very familiar analysis approach, so I'm sure that most of you are aware of what ERPs are. However, just for this analysis part now here, let me just very quickly recap. So what we are usually doing is we are providing a stimulation to our participant, for instance, a visual stimulation as with our checkerboard, and we would expect some evoked activity as a response to this stimulation. However, the brain isn't doing nothing and then just waiting for our stimulation. There is some ongoing activity, also noise, that is there all the time. So therefore, each presentation of the stimulation will be a mix of noise and the evoked activity. And of course, at the time where we have the evoked activity, something else will be overlapping there as well. So therefore, what we usually do is that we present those stimuli of the same category many, many times. So not the same stimulus, of course, but a stimuli from the same type of category. And well, in our case, actually, of the visually evoked potential, we use the same stimulus, but this is a very special thing to do with this checkerboard, of course, where this is possible. And yeah, then what we do is we average through all of these presentations, all of these trials, with the aim to boost the evoked activity and at the same time suppress the noise, the ongoing activity, because this is not time locked. While the evoked activity is. So the non-time locked noise should average out, and what remains is our evoked activity, and this is the ERP. So when we do an ERP analysis, this is what we do. However, we can also, despite the ongoing activity that is overlapping, still investigate the single trials. This is then what we call single trial analysis, and this is what we would rather look into now. An ERP or a trial that is giving some evoked activity based on stimulation has certain features. Tracy has already introduced this in the beginning. So usually for an ERP component, you could look at the latency. So when is this happening with respect to the transformation? And usually we would look either at the onset or the peak latency and the amplitude. So you could look at the amplitude of the peak, or you could look at the amplitude in a time window. And of course, you can also create topographies at certain time points. So it's possible to look at these features and export them from both the ERP and single trials. For our EEG-informed fMRI analysis, we want to characterize, as Celia said, the fMRI based on the trial-by-trial variation in the EEG to get a better prediction. So therefore, of course, we need to use the single trial features here and use them as an additional predictor in the fMRI model. And just a bit more on the practical side, what can we export and how? So one thing, if we're looking at peaks, so for instance, the visually evoked potential that we're looking at is a rather peaky component that is short. There it makes sense maybe to look at peaks, and therefore we can look at the amplitude of the peak and the latency of the peak. So we can look at one of them or both. And if we have maybe a little bit broader peaks, so later potentials tend to be longer and larger, but there are also some potentials that are slower drifts rather. So in such cases, maybe we rather want to look at the mean amplitude in a time window or the area under the curve. So in our example, again, the VEP, we can really look at the peak. So we would go for the first one. The logic in analyzer would be that we have first to find this peak. So we have to detect it and put a marker in its position. And then we can export the amplitude and the latency from this point that is marked in the signal. And how do we do this? There are, in this case, two tools to mention. So the first one is the min-max marker solution that we need to use to locate the peak and place the marker. And the second one is the peak export solution, which is then used to extract the amplitude and latency information from that marked point. In case you're new to Analyzer, you might also not yet be aware of what solutions are. So there is the Analyzer main program, but then there are also small additional programs that can be used for certain computations that are not covered by the main transformations, and those are the solutions. There is an official solutions package available for download from our website, where you also find Analyzer. And this package, you can download it for free, and there are a lot of different tools in there, so not just these two. And a lot of them actually deal with single trial analysis or specific exports and so on. So definitely it's worth downloading this and adding it to your Analyzer. Usually an analyzer is only complete including the solutions package, since there are so many helpful tools in there. Okay, let's now actually use these in Analyzer in order to get out our peak information and use this in fMRI. So I'm switching back to Analyzer. So here we are again. We have applied LORETA to our difference wave of the ERP. However, now I need to go up in the tree because I need to come back to the point where I still had single trials. So I need to go up to this point, the artifact rejection node. That's the last node containing single trials before averaging. Just switching back to our tab view here. So you see actually this has 54 trials, although some of them are marked by that interval. So now the first step, we would have to find the peak in our single trials. And for this, I'm now going to the Solutions tab. So the solutions are not in the Transformations tab, but in their own tab. And here in the Markers group, I have the min-max markers. So if you have done a peak detection before with an ERP, you might be aware of the peak detection transformation. However, we want to detect a peak in single trials, therefore you have to use the min-max markers. Let me just talk you quickly through the different options here. So first of all, you can say, I want to search the peak based on amplitude or on the first or second derivative. The derivative options might make sense in specific use cases. However, most often you are probably going to use the amplitude one, especially if you want to do what I want to do now, which is finding the peak amplitude and latency of an ERP peak or a single trial peak. So I select amplitude. Then the time range. Coming back to what we have done before, we pooled over a few electrodes to get like a nice idea of the timing of this this potential. So this can be helpful to infer what to use here. And I'm actually going just to use 100 to 200 milliseconds, because what we saw is that the potential only starts around 100 milliseconds, and then until 200 milliseconds it should have peaked. And then you can now select whichever channel you like. So what we are going to do is we are not going to use all channels, but we are going to use again our channel P08, just as before. And here we have it. And now we have to decide what we want to detect. So I just want to detect a maximum and not a minimum. So this is because we are looking at the P100, so positive going potential. So therefore I'm going in that direction. And the default here is max. I will just call it P100, which is a bit more clear what it is then. So this is especially useful if you're going to use this more than once, if you want to mark several peaks in the same data. And then I click OK. This goes pretty fast, doesn't take too much time since it's not so many trials. There we go. So now we have our node here, and just calling this P100. And so since I've done this on P08, you will only see the marker on P08. So I have to go down there. Maybe you see it already. Here it is. And if you now just go through the trials, you see how this marker jumps. So it's earlier, then it's later. The amplitude level also jumps quite a lot. So this is now how you can see how there is each trial a little bit different, which means there is quite some variability trial by trial in here, which is exactly what we are looking for to inform our fMRI analysis. So now we have the marker there, but we still don't have a file with the amplitude values and the latency values. So what we need to do next is simply to export this. And for this, we're now going to the peak export solution. So again, we are staying in the solutions tab. The peak export solution is under export here. And this sometimes takes a short moment to open because it has to read quite some information from the data node. And there it is. So the peak export solution can do several things. So what we are going to do now is we define our peak action as peak. And then we can say here, I want a P100 peak. So this is why I had to define the peak first. Otherwise, it couldn't now extract something from a peak. Yeah. So if you don't have defined a peak as we just did, you can instead use the time area and then say, give me the mean amplitude in time window X to Y. Yeah. But in our case, we're using the peak and then define which peak. And then we don't have to do much more. So it doesn't make much sense to say all here because we only have this peak marker in the P08. However, if we would have put it in all electrodes, you could now again make a sub selection and say, just show it to me from the P08 channel. Okay. We only use this one definition of export information here. You could add more, as you can see, and then we have to tell Analyzer where to put this. So it will put it in a file, in a text file. By default, it uses the name of your history file. So that's the EEG-fMRI demo data and the name of the node. So this is what you get here. It shows you the preview of how the file will be called. This is quite useful to use these placeholders here because you will do this export for each data set separately. And if you then later want to use this node in a history template to automate the analysis, it's important that there is some variable naming information in here that identifies the participant, but also the condition potentially. So I actually have not put the condition name in here, but this is something you could still do manually now, or you could just put in a name, but I will only do it once now. But if you would to do it both on the high contrast and the low contrast condition, you would actually have to put this in the name, and then it would also be reflected in the node name here. And then a nice option here also to use is append output file. This is useful if you use it in automation because then every time it reopens the same file and just adds the information. One thing I also want to do here is on the bottom. So I actually don't want to have only amplitudes. I also want to have peak latencies. So the amplitude you get by default, but if you mark this box here, you also get the peak latency. And I click OK. This again goes rather fast because we don't have much data. And there we go. So we have now our peak export, and this goes automatically to the export folder. And I have already my workspace folder open here. So I'm going now to the export folder of this workspace. And here we have the file. You can open this with the text editor. So I show you this file shortly. Here it is. And now you have one line per trial. As you can see, here's the number of segments. And then you have two columns here because we extracted both the latency and the amplitude. The latency is marked by L and the amplitude is marked by V for voltage. And you can also see here now this is for the P1, so shortened for P100 marker, and the P08 electrode. And now you get for each of these trials those values. And one last thing to highlight here is that we have here these rows where we have some empty values. This is actually because we had some trials here where we had artifact markers in there, so those are omitted. And we will come back also to what you could do with these actually in a moment. So let me just go to the slides and just summarize this part. So again, the fMRI analysis now can be informed by features from single trial EEGs, reflecting task variability over time. Many different features can be used. So for ERPs, peak amplitudes, latencies, or mean amplitudes are just common. You could also use something like mean power and specific frequency band. You need to use special tools from our solutions package, so min-max marker solutions for the peak detection and peak export solution for the export. You do not need, of course, the marker detection if you do not want to do a peak export. And lastly, the artifact handling. So since you're using single trials, the ongoing activity is still there. So therefore, trials with large artifacts should be discarded. And the missing trials could then be treated in different ways, for instance, removing them or replacing them by the mean. And Celia will now also come back to this for the actual fusion analysis.
Okay, I'm going to just wait a few seconds for Michael to stop sharing his screen before I start again. Hopefully this will solve my issues. Okay. So we just, well, Michael just exported these data values that corresponded to the P100 voltage values for a high contrast condition. And I will now use this text file essentially and incorporate in my fMRI analysis. But prior to doing that, I just want to point out that during the pre-processing of our EEG data and also during the ERP analysis, there were a few trials that were marked as artifactual, and thus we do not have a P100 value for them. So to correctly reflect the trial-by-trial variability in the fMRI data, we should also consider removing these trials from the design matrix in our GLM model. There are other ways to handle missing information, but today I'm going to focus on just removing these trials from my fMRI data set as well. So what we are going to do in the GLM now is we're going to parametrically model the hemodynamic response based on our experimental parameter that we obtained from the EEG data. Specifically, what we're going to do is we're going to model the amplitude of our kind of response or model functions by integrating that amplitude of the P100 component that we just extracted for each individual trial and using that to model the height of our hemodynamic response. And we can see that in orange as compared to the model functions that we used earlier in our general linear model here in blue. Now, what we need to do is we actually need to set up our design matrix slightly differently. So previously, we modeled the height of each experimental onset as a constant value of 1. And we can see that here by the black stick functions. And that subsequently then resulted in a predicted hemodynamic response, as we see here in blue. Now, in a parametric modulation, we take information from the EEG, so the amplitude values of the P100, and then use that to express the onset of our checkerboard as a ratio of 1 based on the amplitude of the P100 component for that given trial. And then we can see when we convolve that with the hemodynamic response function, then we get a model function that has various heights or amplitudes across our different trials. Then when setting up the design matrix, we now can add an additional column for each condition in our experiment. And this would then result in a P100 modulated high contrast condition and a P100 modulated low contrast condition. Just to switch the laser pen really quick, which we can see here and here in our design matrix. And if you notice that the onset of the P100 modulated high contrast condition is exactly the same as the high contrast condition, the only thing that is changing is really this grayscale value or the amplitude over time. And then we can still choose to include regressors of no interest or nuisance regressors, such as movement parameters, to still account for additional variation within our data that is not observed or contained in our parameter functions here or experimental conditions. And then we would continue the analysis as we did earlier and estimate our parameter weights, followed by performing some statistical analyses, such that we then get these statistical parameter maps. And in this given example, we can see the comparison of high contrast in red overlaid with the P100 modulated high contrast activation here in blue. And we can see that the spatial activation maps for the high contrast and compared to the P100 modulated high contrast condition vary spatially. And at this point, we may want to then ask ourselves whether the spatial activation maps are truly reflecting variability of the participants' behavioral response across the different experimental trials as we modeled it based off of EEG data, or if it's potentially what we're seeing here is still something related to other factors that could potentially explain some of the variation in spatial activation. To maybe summarize what we did in the second example for the EEG-informed fMRI analysis, we used the onset of the neuronal events measured in the EEG data to then parametrically model the trial-by-trial variability in the hemodynamic response and spatially identify brain regions where the fMRI signal is related to that EEG event. We did make a few assumptions, including that the EEG-derived feature that we extracted co-varies with fluctuations in the fMRI signal. More specifically, we assumed that the hemodynamic response is linearly related to synchronous neural activity resulting from the summation of the postsynaptic potentials as captured by the ERP response. However, this does mean we should maybe consider what would have happened if, for example, we had selected a different feature of the ERP component, for example, such as the latency and how that would have affected our fMRI analysis. And we should always consider whether we had strong enough an SNR within our ERP features that we extracted such that we can actually reliably incorporate them into our fMRI analysis. And that would involve considering to what extent we were able to remove artifacts in our EEG data, such as eye blinks, but based on the fact that Michael performed the pre-processing, we can be fairly certain that we removed a lot of the artifact. However, something that we didn't necessarily consider in this particular example are factors such as ongoing oscillatory activity. So Michael already showed earlier that the evoked response to a specific stimulus does vary across trials, and some of that is partially due to just ongoing neural activity or oscillatory activity in that we are also acquiring or that is superimposed on top of the evoked response. And potentially this is something that we should consider also modeling within the GLM to account for some of that variability. We should always consider also that any kind of change with an evoked response or also potentially in the fMRI can always be related to motion-related artifacts. So maybe we should consider whether we were able to remove enough of any kind of motion-related artifacts from our data. And finally, we should ask ourselves whether the bold statistical parameter maps that we obtained in the EEG-informed fMRI analysis is something that we would expect. Would we expect to see some variability across maybe behavioral response or neural response within a subject in different regions compared to just maybe processing of a stimulus? And or could we have maybe increased or our number of trials, and subsequently also increased our effect size within the EEG-informed fMRI data that would maybe have resulted in a different spatial activation map? And keeping these considerations in mind, I would like to just end with a final takeaway. I know we have covered a lot of information today across the 3 webinars, but I would like to end with just a few key points to keep in mind when considering performing an EEG-fMRI analysis. And it really begins with the study design and the data acquisition itself. So already at that stage, we should consider what we want to do with our data and how we want to combine it, because this will very much influence the study design, such as, for example, considering increasing the interstimulus interval if you're using a task-based study design, such that we can account for the more slow-acting hemodynamic response, or possibly also increasing the number of trials that we have, because we know that we have a decreased signal to noise ratio in our EEG data when it's acquired within a scanner, and possibly also increasing the number of trials if you want to do a kind of trial by trial comparison. Then we should also consider how we plan, or first of all, to consider what kind of artifacts we would expect in our data, and then how we plan to deal with these artifacts. So do we plan to attenuate the artifacts, or will we reject them from our data sets? And if we attenuate the artifact, can we attenuate them enough from both data modalities to then kind of continue the combined analyses, or do we still have some residual artifact that is influencing our combined EEG-fMRI analysis? On the other hand, if we consider rejecting trials or parts of our data that have artifact in it, we want to make sure that we do not remove too much data. Otherwise, again, we run into issues of having a smaller effect size and having reduced power within any kind of statistical analysis. Then we also saw a few examples today of how we need to consider restructuring or resampling our data. Particularly in the fMRI-informed EEG analysis, we reduced our fMRI activation maps to 1 peak coordinate, and maybe we should ask ourselves whether that peak coordinate really was representative of the expected peak or expected kind of peak response you would see in the EEG time series, or whether we should have maybe constrained our source data to a larger region, such as the kind of whole cluster that was activated in our fMRI data. In the EEG-informed fMRI analysis, we then reduced our EEG data down to 1 EEG channel and then used that to extract our features of interest that we then used to model or parametrically model the fMRI data. Again, here we might want to ask ourselves whether that channel is really representative of what we expect to see in the fMRI signal, or whether we should have maybe considered pooling data across different EEG channels. And then finally, once we have obtained our results, we should always ask ourselves whether the results that we observe are what we expected, and whether there are maybe other factors that could have influenced or changed our observed results if they do differ from what we expected. And in some cases, this also comes down to considering whether we actually expected a positive or negative covariation between the EEG and the fMRI data. So hopefully, with keeping these kind of key factors in mind, we have provided some more information or better overview of how to combine EEG-fMRI data. And with that, I'd like to end today's webinar series and ask whether you have any questions on all 3 of our webinars.
Great, thank you both again for some excellent talks. We have a few minutes left for some questions, so I would start with one for you, Celia. So you mentioned respiration effects in the BOLD data. Is it possible to model those, and if so, how would you do it?
Sure. Maybe I'd mention that there are possible methods for modeling respiration effects, and we can do this mainly from more of, let's say, a data analysis perspective. But one of the best things we could do is actually to measure respiration within our data sets. A lot of times there are issues when just using, let's say, more clinical devices for measuring respiration rate, because we always have the issue of not having perfect timing between acquiring our fMRI or EEG data and, let's say, some respiration signal. However, it is possible to also record respiration signal within our EEG data or within Recorder, the software that we offer. And one nice thing of having that signal is that we then have perfectly timed respiration or perfectly synchronized respiration data that we can then easily extract from the EEG recording itself and implement within the GLM analysis. And then you would need to possibly downsample your data to match that of the TR, and then you can just easily model the respiration rate, for example, as a regressor of no interest in the GLM.
Okay, great, thank you. And then, yeah, one question for Michael about the LORETA transformation. So, there's a LORETA view in Brain Vision Analyzer. So why would we use regions of interest or defined regions of interest when using LORETA? So I think this is perhaps the difference between the view and the transformation.
Yeah, sounds like. Maybe in this case, I could just show the schematic again that we had earlier. That might maybe help to explain this again. Is an important thing to keep in mind if you're interested in source analysis, may it be in EEG-fMRI or source analysis in general. So here we go again. So yeah, so these are really 2 complementary things. So LORETA as such can be understood as I'm just getting out the time series from certain points in the volume of the source model. Like a certain voxel or many voxels averaged together in a region of interest. That's this blue pathway on the right. And to do that, I need to know where to look simply. So, and that I know where to look if I have information ahead of time. And in our case, the information comes from my fMRI analysis that is just from the recording in parallel, so same recording. So that's ideal, but maybe I have done an fMRI study as a pilot study or like separately, or I use information from elsewhere. But sometimes I just want to maybe be more explorative and don't really know where to look. I maybe just have an idea from looking at the distribution of my scalp maps, but scalp maps do not show you really what's going on in the brain. It just shows where on the scalp, due to volume conduction, those potentials from the neural generators end up. And therefore, in such a case, we can use the red pathway going via the transient transformation LORETA, which just gives us these source activation maps. So then I see for each time point where is actually the maximum of activity in my source model. And this is then just providing me those coordinates where to look that I get for the blue pathway from elsewhere. Yeah. So it's basically just a way to get this input that I need for this blue pathway, because it doesn't make too much sense probably to just blindly get out the source time series of every single voxel separately in there. That would just be like an explosion of data, so to say, and you wouldn't really know where to look at.
Okay, great. Thank you for the clarification. I think that was very useful. Okay, we're right up to time, but we have one last question, which I think is very quick, and I could potentially answer myself, but maybe, Mikhail, you want to add something. So is it possible to add more markers in the EEG continuous data after data collection? The short answer would be yes, using the edit markers transformation. It depends on what kind of markers you want to add, but you can find further information on that in the manual and so on. Anything to add, Mikhail, or that enough?
No, not really. I mean, edit marker transformation is the go-to if you know where to put the markers. If you want to detect somehow where to put the markers, then of course what we just used might be an option. And there are also other tools in Analyzer like the level trigger, for instance, that also allows you to put markers based on a threshold that is surpassed. And other tools even that allow you to put markers based on reference markers. So let's say you have a marker in your data and want to add another marker, always at a distance of 1 second. That's also possible. So plenty of options.
Great. Thank you. So yeah, I think we will wrap up there. We're right on time, which is great. So I would just remind everybody that we have an events newsletter that you can sign up for, and this may be particularly useful for you guys because we have an in-person on-site EEG-fMRI workshop coming up in the UK, in Birmingham in November. That will be officially announced and registration will open in the summer. So do sign up for the newsletter if you want to register for that event. And also just to let you know that the recordings from these webinars will be on our YouTube channel, and that will happen a few days after the event once we've had time to download them and separate them into the 3 separate sessions. So that leaves me to just thank our speakers for today. Thank you, Celia and Mikhail. It was very nice talks and a really good overview of what you can do with integrating these data. Also, thanks to Shiva, who's in the background handling questions and so on in GoToWebinar. And finally, thank you to all of you for attending and also for asking lots of questions. So we will leave it there and leave you to enjoy the rest of your evening. And we hope to see you at another Brain Products Academy event soon. So bye from us.
Bye.
Bye.